start by reminding us, last time we talked about right triangle trigonometry. So we remembered SOHCAHTOA, which says that in a right triangle with acute angle theta, that sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, so on. But we had to remember that opposite and adjacent were always relative to the angle's location in the triangle. So opposite is always across from the angle. Hypotenuse is always across from the 90 degree. And then adjacent is that third side. So depending on where that theta is located, which acute angle, dictates where the opposite and adjacent are. Everybody remember? Okay, and then we said, okay, SOHCAHTOA reminds us that sine is opposite over hypotenuse, that cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Now to add on to this a skosh, you might ask yourself, well, Mr. Kulik, that triangle has three labels, right? Opposite, adjacent, hypotenuse. And we're going to be pairing them together into a ratio. If I have a pool of three things and I want to make pairs out of them, should be 6 ways to do that, right? There's only 3 listed here. Why isn't like hypotenuse over opposite or adjacent over opposite? Why isn't that like a function or a ratio? Well, they are. We just haven't told you about them yet. So those guys all have names. So we have cosecant, which is abbreviated as CSC, which is hypotenuse over opposite. We have secant, which is abbreviated as SEC, which is hypotenuse over adjacent. And then we have cotangent, which is abbreviated as COT, which is adjacent over opposite. So there's actually going to be 6 trig ratios that we're going to worry about. There's sine, cosine, and tangent that everybody seemed like we remembered. And then there's these 3 new ones, cosecant, secant, and cotangent. Now, if I look closely and I compare the ratio for sine and cosecant, what do you notice about those 2 fractions? We have opposite over hypotenuse and then hypotenuse over opposite.
You just flipped it.
Yeah, there's a math word for when we flip a fraction. What's that called?
Reciprocal?
Reciprocal, yeah. So oftentimes these guys are called the reciprocal trig functions. And sometimes we define them then as cosecant is like the reciprocal of sine, or secant is the reciprocal of cosine, or cotangent is the reciprocal of tangent. Right? So either way of thinking about them is fine. And at this point, you're probably sitting here looking at me going, oh, Mr. Kulik, I gotta memorize 3 more of these things? My answer to you would be, not really, because what do you all get to take into your test? Yeah, that half sheet of notes. So if you think you're gonna have a hard time remembering these 3 new ratios, where would be a good place to store them? On your half sheet. Remember we recommended like having that a living document that lives alongside your notes, and as you come across things that like, that's a good idea to put on a half sheet, that you put it on there and you can always rewrite and organize it again later. But like start collecting that information as you see it is usually a good idea. So I'm just putting that out there to remind you guys that we talked about that. Okay. So what I want to do now is I just want to do a couple of example problems. So let's say we have that. So let's say we have this right triangle and we're asked to write the 6 ratio or the 6 trig ratios. So that's asking us to write sine theta equals something over something, cosine theta equals something over something, and so on and so forth, right? So the first thing I'm going to do is identify where the angle is that I'm working with. So my theta that we're using is here. Relative to theta, this side that has the 4 on it is this opposite, adjacent, or hypotenuse? Opposite, because it's across from the angle. This side is with the 6, hypotenuse, which means the side we don't know is the adjacent. How are we going to find that third side that we don't know? The Pythagorean theorem. Remember, if you know 2 of the 3 sides in a right triangle, we can use the Pythagorean theorem. And the Pythagorean theorem says for a right triangle with side lengths A, B, and C, where C is the hypotenuse, that A squared plus B squared equals C squared. So it doesn't matter which leg you call A or B, that part is irrelevant, but the hypotenuse absolutely has to be the C. Right? You guys remember this? Good. Again, good to remind us. It's easy to forget that, oh yeah, the hypotenuse has to be C. The other ones can go wherever. So let's just call this side X for the moment. What equation can I write then to solve for that side X? Yeah, Fadi?
36 equals 16 plus x squared.
Okay. I'm going to write it as 4 squared plus x squared equals 6 squared first. Is that okay? Same thing that you said. I just want to make sure that it looks like the formula for everybody else. Everybody's good? Now to solve this equation for x, the first step would be to isolate the variable. But even before I want to do that, I want to square the numbers, right? I want to simplify those exponents because in the order of operations, exponents comes before addition and subtraction. Before I start moving things to different sides, got to clear those exponents out of there, at least the ones that I can. So 4 squared is 16 and 6 squared is 36. And then we can isolate the x squared. So to do that, we'll subtract the 16 from both sides. And then how do I get rid of the squared on that x? I square root both sides. When I square root both sides of an equation, what do I have to remember to be careful about? Well, we do want to do that, but there's something before that even that we have to be careful that we remember to do.
Negatives.
What's that?
Negatives.
So the plus or minus, right? So remember that we have, when we square root both sides of an equation, that creates a plus or minus. Now, in this problem, what is x representing? A side length of a triangle. Does a negative answer make sense in this context? No. So we can drop that negative. Okay. because negative side length makes 0 sense in a geometric setting. Now, Fadi also recommended that we worry about simplifying this radical, right? Can I simplify the square root of 20? Should say yes. How do I know whether I can do that or not? Because one of the factors of 20 is a perfect square. So remember our perfect squares: 2, 4, 9, 16, 25, 36, 49. You get the idea, right? Which one of those is a factor of 20? 4. So because 20 is 4 times 5, I can think about the square root of 20 as the square root of 4 times the square root of 5. And the square root of 4 is 2. So I'm going to call this side 2 square root 5. Come on. Does everybody feel okay? Now it's time to start answering the question, right? So sine theta is opposite 4 over hypotenuse 6. What do I have to make sure I do here? Yeah, let's reduce that fraction. Everybody feel okay? Cosine is what I'll do next. Does it matter the order that I write these down? No, I'm just going to do SOHCAHTOA and then the reciprocals down the other side. Start with the stuff we're most familiar with. Cosine is adjacent, so 2 root 5, over hypotenuse. What do I have to be careful about? Can reduce again here, right? There's a factor of 2 on top and a factor of 6 on bottom. They both are divisible by 2. So I can just write that as root 5 over 3. Everybody okay with the reducing that I did there? You just kind of ignore the square root and reduce around it, right? Tangent is opposite over adjacent. So opposite is 4. Oops. Adjacent is 2 root 5. Everybody okay there? Again, I noticed that I can reduce. So let's go ahead and do that. And then I also observe that I need to rationalize that denominator, right? I have a radical in the denominator of my fraction, so let's take care of that. So I have 2 root 5 over 5. So far, so good? Stop me if anything's a problem, right? Okay. So the next thing I want to do is cosecant, secant, and then cotangent. Now, I can use hypotenuse over opposite to write down cosecant, but that's not the way I like to think about it. What I think feels easier is just remembering that cosecant is the reciprocal of sine. So if sine is 2/3, cosecant should just be 3 over 2. Right? I don't need to go back to my triangle necessarily to do this. I can just look at the other answer and just flip it, right? So same idea here. I can take the reciprocal of cosine. But darn it, what do you notice happens? Radical in the denominator. So I got to get that out of there. Does anybody remember the name for that process? We talked about it last time. It's called rationalizing the denominator, right? We want to turn that denominator into a rational number. And then cotangent. Now, if I look here, I want to be careful because I have like 3 versions of this answer that I could use, right? This is the one that I'm going to choose to use. Why is that one? Because the radical will just be in the numerator on that one, right? The other one, the first one, I'll have the radical in the numerator, but I still have to reduce. I don't have to do that twice if I don't have to. If I do the last one, I'm going to end up with a radical back in the denominator, so I have to rationalize again, and then I'll have to reduce. That's a hassle. I'm just going to try to make my life easier by choosing the version of the answer where there's no simplification left for me. If we possible.
Sorry.
Go ahead.
There's always going to be one that we can, like, just flip automatically.
Yeah, you can always do it as a flip, right? If you know sine, you can get cosecant immediately, right? Now, like in the case of cosine, there's no way to choose a simplified answer to not have to rationalize the denominator because radicals are in the numerator the whole time, right? But if I start with a radical in the denominator, I know there's going to be some simplified version of this answer that doesn't have a radical in the denominator when I flip. So, again, it's not wrong if you flip it and have to rationalize again, but like, just extra work, you know? Like, my life's hard enough. I don't want to make it harder on myself. Is everybody okay? Okay. So an alternate version of the way I can ask you this question is I can do something like this. So if I give you one of these ratios, I can ask you to find the other 5. Now this doesn't look like the same problem as last time, right? The last one had a triangle, this one doesn't. But it's actually almost the exact same problem. So when I see a problem like this, where again, it's asking me to write down all the ratios, I have one of them. I want to start by translating this statement into a triangle, into a picture. So if I look, the trig function we're given is cosine. If I think back, cosine means adjacent over hypotenuse. So my adjacent side must be 6, and my hypotenuse must be 7. Okay, well, I'll draw myself a right triangle. I'm going to label opposite, adjacent, and hypotenuse. Notice that because I drew my right angle here in the lower corner, opposite and adjacent are in different locations than in the previous problem where the theta was in a different spot, right? Those move around depending on where the theta is. So we know that the adjacent side is 6 and the hypotenuse is 7. And what does this problem now look like? It's the identical problem to what we just did before, right? See, so you do the exact same process. Nothing needs to change. I'm not going to do the whole thing over again because it was kind of a lot of stuff. I just wanted to show you that although this looks like a new kind of problem, all I need to do is translate it into a picture. Now it's the same problem. Just that's the takeaway.
So that's what the question would be. So you would just draw it?
Well, and then you have to finish the problem doing the exact same thing we just did. So I'm just showing you that this problem, this new problem, same as the old problem.
Okay.
You just have one additional front-loaded step where you have to just translate it into the old problem by drawing a picture. So I'm just gonna write this, and we're not gonna actually finish this one. I just wanted to show you how to translate it into the previous kind of problem. Was okay? Just in the interest of time, we have more things that we wanna do today. We did a bunch of practice like this last time, so I don't wanna belabor this too much. Right. Our last example is gonna be a solve the triangle example. So the direction, when we see the direction, solve the triangle, what does that mean?
Final sides, final angles.
Find all the missing sides and all the missing angle measures. So if I look at this, it looks like I'm missing one angle and then two of the sides, right? I'm just gonna label these. Give it some variable names. So I'm gonna call them X, Y, and Z. You can name them anything you want, A, B, C, or alpha, beta, gamma, if you like the Greek letters or whatever. Just taco, pizza, fried chicken, whatever you want to call them. They're just variable names. Everybody's good? Of these three, what's going to be the easiest one to find? X. Great. How am I going to find X?
Just add 32 and 90 to try out.
Great. You can do it that way. You can also just equivalently do like 90 minus 32 since we're in a right triangle. That's a corollary, I think, to the triangle sum theorem is what we called that in geometry. It's been, probably more than 10 years since I've taught geometry, but I think I still remember most of the theorem names from that. Impressed? Probably not. It takes more than that. Is everybody okay there? So we have an answer for X. Okay. Does it matter which one I solve for? Really, X, Y, or Z? Did it matter the order that I did this? No. Right? X was just easy, so I went and took that first. I'm gonna do Y second just because alphabetical order. Doesn't really matter though. So to find Y, I'm gonna choose to use the 32-degree angle. Let me change colors here, because it's a new part. Relative to that 32-degree angle, the side I know is opposite. And Y, the side I'm looking for, is the adjacent. Everybody okay? Which trig function should I use here? Opposite and adjacent. Yeah, good. So we'll write the equation tan 32 degrees equals opposite over adjacent. Now we've translated that picture into an equation. All I need to do now is solve for y. My recommendation to you to think about solving this algebraically is to write this as a proportion. So I'll put it over 1, and then we'll cross multiply. So y times tan 32 is equal to 9 times 1. And then I just divide both sides by tan 32. And into my calculator this goes. And I get about 14.40. Feel good so far? Now we gotta find z. To do this, I'm gonna start very similarly. I'm gonna choose again to use the angle that I'm given. I'm gonna choose again to use the side that I'm given. But this time I wanna solve for side z, which is hypotenuse. So I need opposite and hypotenuse. The trig function I should be using is sine. So I'll write the equation sine 32 equals opposite over hypotenuse. And now I've translated the picture into an equation, so I just need to solve for the variable. I'll think about this as a proportion. I'll cross multiply. So I have z times sine 32 is equal to 9 times 1. And then I divide by sine 32. And then it's calculator time. And I have 16.98.
They don't know that the Western Hemisphere exists, so for them it's like,
You guys feel okay? What we done to here? As a enrichment question, here on this last step, say, we had opposite and hypotenuse, right? We chose to write sine equals opposite over hypotenuse. Well, cosecant has opposite and hypotenuse in it also. Mr. Kulik, could I have done cosecant 32 equals z over 9? Well, that equation is correct, but there's a problem. If you look at your calculator, I see a button for sine, cosine, and tangent. I don't see a button for cosecant, secant, and cotangent. I would avoid using those in doing this kind of a problem because it's not a function that's built into your calculator. So just use sine, cosine, and tangent for these solve the triangle problems, or find the missing part of the triangle. It's not wrong to do the other ones, but getting it to come out of the calculator is a little bit of a trouble. And again, life's hard enough. I need to make my life harder by choosing to do something a way that's harder than it needs to be. Everybody cool? We're going to stop here. So, remember on the first day of class, we talked about our calculator as the two modes for degree and radian, because there's two different ways to measure an angle. There's degrees, which we're familiar with from geometry, and then radians, which most of us probably aren't familiar with. It might have got mentioned briefly in an honors geometry class, but you probably didn't spend a lot of time talking about that. And if you did the traditional geometry class, I'm not sure it gets mentioned at all. So today we're going to talk about like what a radian is, and since we have two different ways of measuring the same thing, you have that almost inherently. The next thing you want to ask for is a conversion factor so that you can translate from one measurement to the other, right? If I measure something in feet and inches, I want to have a conversion that can translate feet to inches or inches back to feet, right? So we're going to define what a radian is, and we're going to develop the conversion factor to convert radians to degrees. Now I'm going to warn you, I'm going to construct that conversion factor from first principles, so I'm not going to just tell you what it is. So I'm going to show you how we figured it out. Would you have to repeat that process of showing me how we figure out how to get the conversion factor? No. You'll just have to be able to use the conversion factor to convert back. Okay? So the showing you where the conversion factor comes from is not something you need to be able to repeat. You just need to kind of, okay, I kind of get the gist of it, that it's like related to this, and okay, that makes sense where that conversion factor came from. Could I repeat this again tomorrow? No, that's fine. You just, so it's not magic. That's what I'm going for, right? Okay. So let's start with the definition of a radian. So we say a central angle of a circle. So remember from geometry what we mean by a central angle. So if we have a circle, and the circle has a center, a central angle is any angle whose vertex is at the center of the circle. Everybody's okay with that? Has measure 1 radian if it intercepts an arc. So when it talks about the intercepted arc, it's talking about this little piece of the circumference of the circle, right? That's the arc that it's talking about. Intercepted means it intersects it with the same length as the radius. So if this is our picture, I cut out this little pizza slice here and put it over here, this angle measure would have 1 radian if the radius of the circle is the same length as that piece of the circumference. Everybody's okay with that? So in a way, this radian measure, we're using a distance, like this radian measure has something to do with this part of a circumference of a circle, right? We're using a distance to measure that as opposed to degrees, which we read off like a protractor or something. Everybody's okay? So what I want to do now is I want to build a conversion factor to go from radians to degrees. Okay? So I'm going to start by trying to figure out a relationship between this angle measured in radians, the radius, and that piece of the circumference, that arc. Okay? So what I'm going to do is I'm going to build 2 concentric circles. Concentric means they share the same center. I have the little circle that's centered at A, and the big circle also centered at A. Okay? I drew an angle. Notice that this angle, GAE, is the same angle in the little circle as it is in the big circle, right? So it has the same angle measure. Everybody agree? Okay. This is going to be my key observation. If I look at this arc length, this arc length E, and then I look at my arc length P, what do I notice about the relationship between those 2 arc lengths? One is 0.9, the other is 1.8. See anything common between those 2 numbers?
P is 2 times over E.
Perfect. P is 2 times E, right? Because 0.9 times 2 is 1.8. If I look at the radius of these 2, the radius of the smaller circle is 2, and the radius of the bigger circle is 4. What do I notice again? It's also double the size. So maybe I think to myself then, okay, well this angle measure, well I say to myself, okay, if I take arc length and I divide it by radius, for both situations, I should get the same answer for both, right? Maybe that's what my radians, or the measure of this angle is in radians. So this is our takeaway, that the angle measure in radians is arc length divided by radius. That's our takeaway. Okay. Okay, perfect. Now that I have a way to relate my angle measure to arc length and radius, I can calculate a angle measure in radians. For angle measure in degrees that I already know and like kind of use those to figure out a conversion factor. So typically what we want to do is when we have something like this, we want to normalize it. Normalize is the fancy math term for like make this simpler. So the way we do that is we say, okay, what if we're just working with a circle of radius 1? So this radius just kind of turns into a 1. Okay, we're just going to use a circle with radius 1. Everybody's okay? In that case, the angle measure is just equal to arc length. You see how this is going to make our life a little bit easier? So I drew myself an example circle with radius 1. I drew in an angle, the angle DAC. How many degrees is that angle DAC? 180. Wonderful. How do you know it's 180?
Because
It's half a circle, right? A circle is 360 degrees, so half of it is 180. Okay. And then in radians, since this circle has radius 1, the measure of angle DAC is just going to be the length of this arc DAC, right? Everybody's okay? Or, I'm sorry, the length of arc DC. I don't have the third letter there. How much of the circumference of the circle is that arc DC? How much of the circumference? You know, we're talking about that. Half, right? You guys can see that? Okay. And I know the circumference of the circle is 2 pi r. And I know in this circle, what's my radius? 1. Okay. So 2 pi times 1 is 2 pi. 2 pi times a half is pi. And that's what we needed. That's our conversion factor. 180 degrees is equal to pi radians. Just like 1 foot is 12 inches, or 1 inch is 2.54 centimeters, or 1 mile is 5,280 feet, or 1 mole is 6.022 times 10 to the 23rd particles. It's our conversion factor to move back and forth between degrees and radians. That's the takeaway from today. This formula and this conversion factor. That's what we need. Scoop through that. Let's burn through a couple of examples real quick. Really only going to worry about these first 3. I don't think we'll have time to get to that 4th one. So our first example asks, how many radians are in 90 degrees? So I'm going to do this problem just like I would a unit conversion in my chemistry class. So I'm going to start with 90 degrees, and I'm going to think about that as like a fraction over 1. And when I multiply this, the conversion factor, since I have degrees in the numerator, where does degrees have to occur in my conversion factor? In the denominator, right? They have to be on a diagonal from one another. So I'm going to put 180 degrees down here. And I know my conversion factor relates 180 degrees to pi radians. So that's going to go on the top. Everybody feel okay? So when I multiply, the degrees on top and the degrees on bottom will cancel out. That leaves the unit in radians. Everybody feel good there? And then I know 90 goes into 180 2 times. So I'm left with then pi over 2 radians. How do we feel about that? Just like a unit conversion in your chemistry class. Have we all taken a chemistry class at some point? Probably almost all of us. Okay. All right. Here we have pi over 3 radians, and we want to convert that to degrees, so we're going the opposite direction. So I'm going to start pi over 3, and I'll put radians in the numerator. Since radians are in the numerator, in my conversion factor, where does radians need to go? In the denominator, on the diagonal. So we'll put the pi radians down here. So in top, what has to go? 180 degrees. Does everybody feel good? Okay. I can cancel my units, so I know that my answer is in degrees. Pi can cancel with the pi. I have a pi on top, pi on bottom. Those cancel. And then I have 180 over 3. That reduces down to 60 degrees. Does that feel okay there? Okay. One more example and we'll stop. Okay. Part C says, find the length of an arc intercepted by a central angle of 1/2 radian in a circle of radius 5 inches. Oh my gosh, Mr. Kulik, this is like a whole thing. Well, I'm going to draw ourselves a picture. So here's my circle. Here's my central angle. Here's its angle measure of 1/2 radian. And it says its radius is 5. And I'm going to call that arc S. That's the traditional letter we use to represent an arc length, as we use the letter S. You could call it X though, it's fine, whatever. Radius, angle in radians, arc length. How are those all related together? This guy right here, right? Angle measured in radians is equal to arc length over radius. So I have angle measure in radians equals arc length over radius. To solve for S, I just need to multiply both sides by 5. Done.
Good afternoon, Notre Dame.
Perfect
One
time.
quick announcement for the high school. Attention swimmers, the meet today that was scheduled for Holly has been canceled, so there is no meet. There is also no practice. Athletics encourages you to work ahead on your homework.
Paula and Olivia.
And now, let's stop
Get
and
your
close our
IDs.
eyes and take a deep breath as we reflect on the day.
We can put it in a
How
different
have I
way.
used my unique gift
Yes.
today?
Because you're coming back.
Dear Lord, as I look forward to the rest of the week, please present me with opportunities to make someone smile and feel good about who they are. And I ask this in the name of the Father, the Son, and the Holy Spirit. Amen. Have a great day, Notre Dame. God bless. Keep your shoes. You are ready.
You still are coming back for your classwork.
I need to come back.
I'll take that. If you are done, let me know. Are you, Nicole, are you?
No, I'm not done, sorry.
You're not done? Okay.
Yeah.
If you're not done, I'll take those. And Holly, you were finished? You put in the finish file? Okay. Very good. Yes. You're done?
Oh, did I put my name on?
Yes, you do. Are you done? Yes. Thank you.
What's their homework for today? The Delta.
You should work on the 4-2 delta,
Okay.
if you haven't done that yet. That should be, I didn't mention that, I should have. Wish you would have asked me before everybody ran out.
Sorry.
That's okay, it's not your fault, it's my fault for forgetting.
Thank you.
You're welcome.